very much, Chris, and thanks for the opportunity. Thanks to the organisers for inviting me here. Tim and I are going to do a bit of a tag team, and I'm going to start out with part one, and let's just pose some questions from the perspective of what's going on today in contemporary climate change, and how might information from the past help shed some light on where we are now and where we might be going. So my presentation comes in 4 parts. 3 very important questions. We're seeing changes now. How important is human influence versus natural variability? Very common question that's asked. How sensitive is the climate to the forcings that are now due to human activities? Thirdly, tipping elements, abrupt changes in the Earth system and the climate system. Let's just take a look at some of them, and in particular look at polar ice sheets in high latitude regions. They're exceptionally important, and Tim's going to say a lot more about those when he gets up. And my last point is actually going to be a little bit more exploratory, looking at some science that really hasn't come to maturity yet, but is very important. And that's looking at the Earth as a whole, not just parts of the Earth, but the Earth as a whole as a complex system. So let's dive into this. We can see the observations today. There's global air surface temperature record for the last about 140 so years from 1880. You can see a lot of variation from year to year, but the trend over the last half century is clear. Scientists like to smooth that out a bit, and that's an 11-year running mean, that data set I just showed you. And it shows the underlying trend much more clearly, and it's not so dominated by interannual variability. But scientists don't always look at the atmosphere. We look at other things too. There's Arctic sea ice, the ice that floats over the Arctic Ocean. That's been dropping over the last several decades as well. And 2 very important records because they have to do with the ocean. And about 90% of the extra energy at the Earth's surface that's generated by the extra greenhouse gases is actually going to the ocean, not the air and not the ice. This is one measure of that sea level rise. You see the sea level's been going up again since 1880, but the rate has increased the last few decades to about 3 millimeters per year. We can measure that pretty accurately because we have satellite altimeters, and that's what that red line is at the end of the record. And this is a really important record here. That's a record of ocean temperature or ocean heat content. As I said, that's where about 90% of the extra energy is going. And again, that shows a very, very clear warming trend over the last 50 years. So the question is, what's really behind these trends? We know the physics of greenhouse gases very well. There's a very strong consensus in the scientific community that that's what's causing it. But perhaps some information from the past can help us shed light about how important is longer-term natural variability in these trends. The second concept I want to talk about is sensitivity of climate to radiative forcing. In other words, to different factors that affect the energy balance at the Earth's surface. There could be a number of factors. There could be changes in the input of solar radiation. There could be volcanic eruptions which put aerosols into the atmosphere. There could be changes in the albedo of the Earth's surface, or there could be changes in greenhouse gases in the atmosphere. The point is, though, that this is a system property. Whatever's perturbing the system triggers feedbacks or influences feedbacks, and those have to be taken into account when you look at how the system itself is going to respond. The other point to make is that this is a property that's measured when the climate system is at equilibrium. A lot of people make that mistake by trying to back out an estimate of climate sensitivity from what's happening today. And you can't do that because the system is far from equilibrium. We're in a strongly transient state at the moment. So in a way, this is really a scientific concept that's important for us scientists. It's less important for the policy people because they want to know what's happening now and what's going to happen over the next few decades, and not so much what's going to happen millennia into the future. And it's probably taken millennia for the climate system actually to achieve equilibrium again. But when we look at what we call the fast feedbacks from the initial perturbation, and let's say, of course, that we have increases in greenhouse gases, we know the radiative properties of the greenhouse gases. We know that a doubling, for example, of CO2 will raise the average temperature of the Earth about 1 degree Celsius. But the real important thing is, what are the feedback effects that are going to modulate, change, amplify, or dampen that 1 degree? The 2 most important are what we call the fast feedbacks, and Tim's going to talk about some of the slower feedbacks, which are very important in the long term. The important one is water vapor. We know that that's a very strong greenhouse gas. That's a very, very short-lived greenhouse gas. If you like, it's a slave to the longer, the greenhouse gases with longer residence times, like CO2. So as we increase something like CO2, we activate or increase the hydrological cycle, which means we get more evaporation of water as the sea surface temperature rises. We get more water vapor in the atmosphere, and we tend to get more rainfall. It's an activation of the hydrological cycle. That's well known because if you go to the last glacial maximum, when the temperature was much lower of the Earth, about 5 degrees lower, there's very good evidence that the hydrological cycle was much dampened compared to today. So that's one of the most important feedback effects, and we know it really well because we can measure the increase in water vapor in the atmosphere, and we can calculate that about a 1 degree temperature rise caused, say, by CO2 will cause an additional approximately 1 degree by the additional water vapor in the atmosphere. So that gets us to 2 degrees. The second and the more controversial one, the one that we have a less solid handle on, is what happens to clouds. Because clouds can act both ways. They can act to further amplify the warming, but they can also act to dampen the warming. And this was a big source of controversy and uncertainty a couple of decades ago. We've done a lot more work since that. We actually have a few decades of observations, perhaps not long enough, but they're giving us some clues. And it seems to be that most of the evidence now points to the clouds as being another amplifier in general. Thought to be around 1 degree further warming for a 1 degree increase due to CO2, but there's a lot of uncertainty around that. So what do we do then? We take climate models and we try to model these feedbacks that you see here in the physical system. And the ones I've been talking about are fast reinforcing feedbacks, changes in water vapor, which tend to increase temperature, which tend to cause more increases in water vapor as you get more evaporation. Same thing with the gases, the greenhouse gases. CO2 increases temperature, which leads in the long term, and these are slow feedbacks, to more CO2. Now we know that naturally the Earth is triggered by these feedback, it triggers these feedback loops through changes in orbital forcing. That is what the triggers are for the ice age interglacial oscillations of the late Quaternary. But those orbital fluctuations on their own are very, very small. They're not enough to drive the 5 degree temperature change we actually see between an ice age and a warm period. That's driven by these reinforcing feedbacks, both the fast feedbacks and the slow feedbacks. So when you look at this from a systems perspective, it actually doesn't matter whether you enter the feedback loop via the orbital fluctuations or some other perturbation, for example, greenhouse gas emissions from human activities. That will also drive this feedback loop in this direction in terms of increasing change in temperature, increasing water vapor, and so on. So if you take a systems perspective, we can get a much better understanding of how climate sensitivity arises from various perturbations. And this is why when there are other perturbations to the system, like we've seen in the past, we can try to get estimates of what climate sensitivity was in the past. And Tim's going to give you a lot more information about that. In the contemporary period, the way we try to estimate what climate sensitivity might be is to actually run climate models that have those feedback loops built into them. They have the fundamental physics of the greenhouse gases and changing radiative forcing, but they also have the response of the hydrological cycle, and they have the response of clouds and so on. And so when you run climate models and try to back out and run them to equilibrium and try to back out climate sensitivity, what you get is that it's very likely to be under 2 degrees. And we know that well, because we've got the degree from the CO2 warming, we've got the degree from the water vapor feedback, which we know very well. It's also very unlikely to be much above 4.5 or 5. Most of the models show most likely probability sitting somewhere between 2 and 4.5. And the best guess that most climate scientists use is somewhere around about 3 degrees for a doubling of CO2. Let's go to part 3, and that's these tipping elements in the Earth system. I think a lot of you who have looked at climate model outputs have seen these very smooth graphs of projected temperature rise up to 2100, and of course it goes on beyond 2100, but you see for low emission scenarios maybe something around 2 degrees, high emission scenarios something around 5, and various values in between. But when you look at those, there's sort of a false sense of security that those are smooth functions. You don't see much abrupt change, but in fact we know the Earth system is punctuated by much nonlinearity and a lot of abrupt change. That is actually the norm. That's the rule rather than the exception. And scientists have done some work on what some of these abrupt changes might look like. And they involve the ecological systems like the Amazon forest. They involve the ocean systems like the thermohaline circulation. They certainly involve the big ice sheets, the cryosphere, and Tim's going to talk a lot more about that. They involve biogeochemistry, like methane outbursts and so on. So I'll just talk very briefly about a few of these. We can start with the cryosphere, and of course the big interest now is in the Greenland ice sheet and the West Antarctic ice sheet. There's some good paleo evidence that Tim will talk about that during the last interglacial in the Indian, there was significant ice loss from these two ice sheets, and we're moving rapidly into the same sort of temperature change that we saw during the Indian. And there's also some more recent work that's quite interesting about the East Antarctic ice sheet. I won't talk about that very much, but this is an area I think that requires a lot more future research. So what's the stability of that? But we look at the data that we have now, and this is mainly from satellite measures, gravimetric measurements, and also altimetry. They seem to be showing that we're losing ice in a net sense from the West Antarctic ice sheet here. The East Antarctic ice sheet, at least at present, seems to be generally stable. The one that most people are concerned about, at least initially, is the Greenland ice sheet. Some of you may have seen recent NASA images. I won't show them here, but they only came out a week or so ago, showing that virtually the entire surface of Greenland is now melting. It's the first time this happened in quite a long time. But here I'm showing areas that show surface melting, or actually net loss of ice. It also includes discharge. Those are the warm colors. The cool colors are where massive ice is actually accreting due to increased snowfall. The overall balance is shown in this graph. And as we go from 1990 to the present, you see this is the zero balance of no net gain or loss of ice. There's been a net loss of ice at an increasing rate, and now it's somewhere around 200 or 250 cubic kilometers per year. Ice is being lost from Greenland. This is now a significant factor in sea level rise when you look at the sea level rise budget. So this is one of the big uncertainties. It's one of the big tipping elements that we could see a so-called point of no return this century, where the forcing on this in terms of increase in temperature reaches a point where the ice sheet will basically irreversibly disappear or almost disappear. It will probably take millennia to do that, but the tipping point could come this century. The other one I want to talk about is this biogeochemical tipping point, which is permafrost methane. And the issue we're talking about here is a very large area of the northern hemisphere, northern high latitudes, mainly in Siberia, some in Alaska, some in northern Canada, where there's a large amount of carbon material, carbohydrates, that are actually frozen in the upper layers of the soil. And the landscapes look like this. They tend to be very flat. They're above the tree line, above the boreal forest. They tend to be very boggy, very wet. And the soil tends to be frozen for all but about 3 months of the year. And the so-called thawing depth only gets down to 30 to 50 centimeters. This is basically frozen soil. If you do a slice through that soil, it looks like this. You can see a lot of frozen material. But in with that frozen material is a lot of carbonaceous material too. It's locked away from the atmosphere now. It doesn't react. But as the high latitudes are warming, we're starting to see some changes already here. There's a lot of carbon there. We've estimated that it's about 1,500 or so petagrams of carbon. And if you know the carbon cycle, that is about double the amount of carbon that's in the atmosphere today, naturally, and the additional 35 or 40% of carbon from human activities. This is actually a very, very big ticket item in terms of the carbon cycle. So if we look at the temperature change across the world in the last 4 decades, and I'll just flip through it decade by decade very quickly, you'll see how uneven it is. And this is important for these tipping elements, because these tipping elements are in geologic or geographically specific areas. And so it matters for them what the regional rate of warming is. So this is the 1970s. And again, the cool colors are below the 1961-1990 average, which we use as our baseline there, and the warm colors to the right are increases from that baseline. So that's the 1970s, there's the 1980s, there's the 1990s, and there's the most recent decade. So you can see the skewness in warming, that the northern high latitudes are warming quite a bit more strongly than the rest of the planet. And if we can just do a latitudinal graph here, minus 90, of course, being the South Pole, plus 90 being the North Pole, and you can see that the temperature rise is highly skewed. It's about double, or even a bit more than double the global average up at the northern high latitudes. And of course, this is where that permafrost methane is. This is where the issue is. Now, some experts have looked at this and said, well, depending on how strong the warming is actually going to be,
you can release anywhere from 30 to 60 gigatons of pentagrams, all the way up to something like 5 to 800 by 2300 under a high warming scenario. And this compares to about 10 gigatons of carbon, which is the human emission of carbon gases just now. The interesting thing is there's another possible reinforcing feedback, and that's if the decomposition rate increases to the point where heat cannot be lost as fast as it's generated. It'll actually build a reactor into the permafrost soil, the so-called compost bomb, which would greatly increase the rate of loss of either CO2 or methane, depending on that toxic or anoxic conditions. This is a good example of reinforcing feedback, which isn't yet included in any of the climate models, but it could be the type of feedback that we saw, for example, during the PETM or something like that. I want to close now by just taking a quick tour of Earth as a complex system, the whole Earth as a single system, not parts of it as systems, but the whole Earth as a system. And we can see systemic type behavior quite clearly. This is the Vostok ice core, where we have a temperature record for 420,000 years, but we also have records of two greenhouse gases. There's CO2 and there's methane. And you can see some very cyclical type behavior. It jumps out at me very quickly. The first thing we can say is that there are basically two states of the Earth system during the late Quaternary. Most of the time, it's in a glacial state or moving into a glacial state. Fairly erratic climate during that time. And then we have the interglacial warm states, which are very good for us humans. And by the way, humanity, fully modern humans, evolved about in here. So our entire existence as a species on the planet is encompassed in this graph. This is why the late Quaternary, why the last couple of cycles here are exceptionally important. This is what our physiology is evolved to live in, not the types of climates we've seen in the deep past. So we have two states, and it oscillates between these two states. The other thing we notice quite clearly is a thing called limit cycles. Now, what do we mean by that? It means when any of these parameters cycle between the two states, they cycle within strict limits. CO2 goes from a little under 200 to nearly 300. And it doesn't vary very much at all out of that over 420,000 years. And actually back to 800,000 years. And if we look at the other greenhouse gas, we have the same thing. It operates within tightly constrained limits. This is not due to the orbital forcing of the sun. This is due to the internal dynamics of the Earth system. And if we look at temperature is the same thing. It oscillates with a band of about 5 degrees of global average temperature, 5 to 6 degrees. Now I'll put on here where we are now with CO2. And that blue arrow there is actually, the length of that is adjusted to represent where we are today compared to the limit cycle. We can do the same thing for methane. That's that green arrow. So we've actually pushed the Earth system as a whole well outside of the operating range of the biogeochemistry. Of course, the critical question is how is the climate going to respond to that? I think Tim is going to elucidate on that a little bit more. The last thing is the phase lock. You see this cycling between ice ages and warm periods occurs at fairly regular intervals, roughly 100,000 year intervals. Now this is triggered by one of the orbital parameters of the Earth orbiting around the Sun. There are two others, one at about 40,000, another one at 21,000. Phase locking means these are very weak forcing factors, actually. They lock in because of the natural dynamics internal to the Earth system. We believe here this is the waxing and waning of the great northern ice sheets, that they take on an order of 100,000 years to grow after they retreated back to the interglacial. And so this locks in with a 100,000 year mode of orbital forcing rather than the 40 or the 21,000 years. So I want to conclude then by just taking a very speculative look about what complex system science has to say about the Earth as a whole. There hasn't been much research on this, there needs to be much more. So what I've taken here is a roughly 2,000 year temperature record from the northern hemisphere using proxy temperatures back to 1880, and the red line there is the instrumental record of the last century or so. Now I've put the IPCC projections on top of it. Those are the model projections given our present understanding of the climate system. Now those are the smooth lines that you normally see out to 2100. But 2100 on this time scale only comes out to here. So you see this is a huge change in terms of the Earth system, in terms of the biology, the ecology, and in terms of our own physiology. Now the interesting thing here is that if we look at where we are now, this is where we're already committed to just from inertia in the system. If we could reduce emissions to zero tomorrow and allow the system to come to equilibrium, we'd be at about 1.5 degrees about where the Union was, the last bit of glacier. And we can't do that, so we're going to go higher. The worst case scenario really raises the question, really, if the system moves to a new state. We know it's been ice-free. We know it can be quite happy in an ice-free state for millions of years. Can we possibly trigger it eventually in an ice-free state? I'd make a note here from a policy point of view. This is really a severe challenge to contemporary civilization to deal with this magnitude of change and this rate of change. So what are the implications of this new geological epoch, the Anthropocene, that we're entering into? Well, the policy challenge now is, can we cap the temperature rise to somewhere around 2 degrees? And in this case, complex system science says there's a very good chance that the damping feedbacks will still be strong enough to pull us back down to a Holocene-like state. It may take hundreds or thousands of years to do so, but the odds are we'll be capped. But is there some planetary bifurcation point where enough of these other feedbacks, like the methane permafrost, like the ice sheets, all tend to move in the same direction, which is what a complex system does, and move the whole system into another state? We have no idea whether there is one or where it is. The possibility does exist that we could end up transitioning to a new, much higher state that we would be in for hundreds of thousands of years. So this is why this long-term perspective is very important to contemporary climate change, which in turn is very important for policy. So I'm going to stop there because the bulk of the talk should be turned over to Tim, who's now going to try to answer a lot of these questions and provocative suggestions from some knowledge we've gained from past climate change. Thank you very much.